So welcome to this fourth lecture in the series. In the last lecture, we saw how you can start to explore potential energy landscapes by doing an energy minimization to find a local minimum, or a global minimum if you're very lucky. And once you're at a local minimum, or any sort of minimum, then you can do normal mode analysis in order to investigate the motions of the system at that minimum. But that gives us information only about the single minimum. We want to find out information about the overall energy landscape. This is important because the energy landscape as a whole gives you information about conformational space and also structural and thermodynamic information about the system. If you have molecules with tens of atoms or more, then a systematic study is quite difficult. But when you get to even larger systems, a systematic study becomes impossible. So you can imagine an energy landscape like this. There's no way you'll be able to explore all the points on this complicated energy landscape. So when you get to macroscopic samples, so even things like proteins, then you need to use sampling methods in order to explore bits of the energy landscape, but in the right bits and enough bits to make sure that any calculations or predictions you do are correct, or at least sufficiently accurate. An example of a sampling method is calculating pi. So it's not related to biomolecules, but it's a useful thing to discuss. Imagine you put a circle in a square, and then you cut 1/4 of the circle. This gives you a square of side r, and then the circle has radius r. If you now throw darts at this square, then if you think about it a bit, your darts are going to land somewhere in here. Then the number of darts which hit the shaded area divided by the number of darts inside the square as a whole is going to give you a measure of the area of the shaded area divided by the area of the square. So now if you use your knowledge of the equations for the area of a square and the area of a circle, the area of the shaded area, so this quarter of a circle, is the area of a circle, pi r squared divided by 4, and the area of the square is r multiplied by r. So if you count this ratio of darts, then this gives you a value for this. If you then rearrange it, then pi is equal to the number of 4 times the number of darts hitting the shaded area divided by the number of darts hitting inside the square. So you can imagine if you throw just 10 darts at this square, it's not going to be a very accurate value of pi. But now if you throw 1 million, 2 million darts at this square, you're going to start to get a fairly good approximation. So yes, the approximation becomes more accurate with more darts. And this is how sampling works. So if you take more samples, you get a better value of whatever you're wanting to calculate. So when you're looking at biological systems, there are 2 main sampling methods that are used. And whichever method you use, if you do it correctly, then you can actually calculate thermodynamic properties. So you can calculate, for example, free energies, or free energy differences rather. And you can calculate all sorts of thermodynamic properties. In practice, what you do is consider a small unit of your system. So you might want to consider just one protein as an approximation for lots of protein in solution. You can generate lots of replications of this system, so you have lots of boxes with a protein in. And then if you take averages over all these boxes, which are all slightly different, then this will give you thermodynamic properties. And this is so-called the ergodic hypothesis, which says if you make enough replications, then you get the actual answer. And there are a variety of different ways of making these replications, and these are different sampling methods. once you've done your replications, you can calculate the thermodynamic properties using statistical mechanics, and I'll prepare a separate a handout for statistical mechanics, which we'll discuss in the classroom session. Right, but there are two main sampling methods. The first one of these, which we're going to talk about, is Monte Carlo sampling. And this is basically a random process for calculating the properties of a system. So we basically generate configurations of your system, so configurations of your biomolecule, conformations of your biomolecule, which are not connected in time, so you just make random changes to your system and depend only on the previous configuration. So you've got one conformation, you calculate the energy, you make a random change, and then you calculate the new energy, and you continue this. This is generating lots of samples of the system, so you're getting conformations and their energies, and then you can calculate thermodynamic properties. So the way this works is you randomly generate 3n coordinates to start with. So you set the x, y and z coordinates of all your atoms in your system. You now calculate the potential energy of this system using your force field. And now you need to calculate the Boltzmann factor of this potential energy. So this is exponential minus the potential energy divided kT. As you generate samples and conformations, you calculate the sum of the Boltzmann factors and the sum of the Boltzmann weighted potential energies, which allows you to calculate your thermodynamic properties. And you just keep going until your answer is converged. So this is a decision that you as the user need to make. When your answer is converged enough, you stop sampling. So you might do 10 million samples, you might do 100 million samples. It just depends on your computational power available and the accuracy to which you want to know the values. Right at the end, you can calculate the mean potential energy. So that's defined by this equation here. So on the top, we've got the sum of the Boltzmann weighted potential energy. So here's the potential energy, which is weighted by the Boltzmann factor. And here on the bottom, we've got the Boltzmann factor. And if we work out this fraction, so we've collected these during our simulation, we add them all up, we divide them, this gives us the mean potential energy. And we can also use similar equations to calculate lots of other thermodynamic properties. Now, this Monte Carlo algorithm isn't very efficient because you'll have noticed the first step was just generate 3n random coordinates. Now, we know that biomolecules aren't just random configurations in space. Various atoms do need to be close to each other because they're connected by bonds. So there's a revision to this Monte Carlo algorithm called the Metropolis Monte Carlo algorithm, which biases the sampling of these conformations to low energy conformations, so ones which are actually going to be physically meaningful. So these states with low potential energy are going to be the ones which are relevant to a biophysical system. The way this works is we actually add an extra step to the algorithm. We've got one conformation, and now we want to make a new conformation. The Metropolis algorithm has a step in which decides whether, when we go from an existing conformation to a new conformation, do we accept it or not. The previous algorithm just automatically generates a new conformation and you move on. Here we've got a decision to make. So we will accept and move to the new conformation if the new configuration is lower in energy than the previous one. So if it's lower in energy on the potential energy surface, we will take that step. We'll go to a lower energy structure. If the energy is higher, the potential energy is higher than the current energy, then we might accept it. And whether or not we accept it depends on the Boltzmann factor of the energy. So we'll work out the exponential of the difference in energy between the previous conformation and the new conformation divided by kT. And if this this exponential Boltzmann factor is larger or equal to a random number chosen between 0 and 1, we'll accept it. But if it's smaller than this random number, then we don't accept it. We go back to the previous configuration and we try and generate another configuration, which we then may or may not accept. This modification makes the algorithm more efficient, makes it sample lower energy conformations, and it will converge more quickly. So, Monte Carlo simulations for biomolecules will all use the Metropolis scheme. The first thing you actually need to do when you set up a Monte Carlo simulation is choose the type of moves. We don't want to, for example, just move atoms at random. What we might want to do is translate parts of the molecule. So we can move one bit of the molecule with respect to another bit. We might want to rotate parts of the molecule. So we might want to rotate about a backbone bond. So in a protein, if you want to rotate about the peptide bond, it will change the configuration. If you're modelling polymers, you might want to include reptations. This is like motion like a snake, so you move along a path like a snake. You can also have crankshaft type motions. This is where you have, for example, a U-bend in a system, and then you rotate the U-bend about an axis. So all these types of moves are possible. Another thing you need to think about when setting up a Monte Carlo simulation is to choose the maximum size of the move. If you make the size too big, then you're more likely to go from a sensible configuration to a configuration which has much higher energy as parts of the molecule crash into each other. So that's bad, we don't want that. But if you make the step size too small, then you'll be generating structures which are very similar to the previous one, and you're not going to sample conformational space very quickly, and that's going to be computationally inefficient too. So you set up a Monte Carlo simulation, you decide what types of moves you're going to do and then the size of the moves, and then you just keep simulating until your observables, things that you want to measure, have converged, and at this point you say it has reached equilibrium. So these are snapshots from some Monte Carlo simulations. So we can see between 0 steps and 20 steps things have changed a little bit, but then when we get to 220,000 steps we can see there aren't that many changes. So by this stage our observables in terms of, for example, size of islands on the surface have probably converged. But each simulation is different, and you need to just keep going until whatever you're looking at has converged to a stable value. And this you will do by doing some analysis of the simulation. You can actually analyze simulations while they are running and decide whether you need to let it keep going or whether it's done enough. So Monte Carlo simulations is one type of sampling method. The other main one that is used in biomolecular modelling is molecular dynamics simulations. In molecular dynamics simulations, you generate conformations of the system by solving Newton's equations of motion. So we have the equation F equals ma, so the force equals mass times acceleration. So if we have a structure, we have forces acting on various atoms, generating an acceleration, and it means these will move. So we can calculate the structure of the molecule at a certain time step later. In practice, we do this by solving these differential equations. So we have the second derivatives of the position with respect to t is equal to the force over the mass. So by using the force field, we can calculate the force on each of the atoms. We know the mass of all the atoms. So this gives us this term, so d2x by dt squared. So this is the acceleration. So once we know the acceleration on an atom, we can calculate where it would be a small time step later. And that's effectively what happens. You could imagine now a very simple example, so that of hard spheres. So if you've got a box of hard spheres which don't interact, so you can imagine a box of snooker balls, you set them all moving at the start, so they've all got initial velocities. If these are hard spheres not interacting at all, these spheres will just keep moving until they collide with another sphere. So by looking at the motion of all these spheres, you can work out which pair is going to collide first and work out when they're going to collide. In this case, you can fast forward to that step, calculate the positions of all the spheres at that time of collision. Then you know that after a collision, the spheres will have new velocities because they'll bounce off each other. So those two will have new velocities, and then you can just keep doing the same. Identify the next pair of spheres to collide, and then fast forward to that collision time. And this will allow you to model spheres bouncing around, which is a reasonable way of modelling something like a noble gas. So these gas atoms will diffuse around, bounce off each other, and so on. In practice, if we're going to model biomolecules, we'll be using a force field, so like charm, and we can't fast forward until collisions because that's too difficult. So we'll solve the equations of motion numerically. So if we know the positions at one point, we can calculate where all the atoms will be a small time step later. We're not going to look at the details of the maths going on here, but one example you might read about in the literature is the Verlet algorithm. The key thing with molecular dynamics is you need to choose a time step. So again, like with Monte Carlo, if you make the step too big or too small, then it's inefficient. With molecular dynamics, it's a time step now, just not a step in space. And if you make the time step too big, then atoms will have moved too far and the structure will no longer be sensible. But if you make the time step too small, they will have moved too little, and then you're calculating lots of time steps where nothing really happens. So you've got to get a balance. And this time step will depend on the system that you're modelling. And the key thing is to consider the time scales of motions. So we'll discuss this in the classroom, the time scale of motions of biomolecules. So if you want to set up a molecular dynamics simulation, first of all, you need to generate a low energy configuration. You decide on your time step, and then use assign velocities. So you start all the atoms moving with a certain velocity. These velocities will define the temperature of the system. You might want to gently heat from 0 Kelvin to 300 Kelvin, so start them moving very slowly and then gradually allow them to speed up. Or you might start it at one temperature and then scale the velocities to move to another temperature. Once you've got all the atoms moving at the temperature at which you wish to simulate, then you just keep going. So you've got one structure, you make a step in time, then you generate another structure, and you've got the energy of the structure, and then you keep going. And then using statistical mechanics, you can use all the energies of the structures to calculate thermodynamic properties. And once again, you will need to just keep going until the simulation converges. So we've seen molecular dynamics and Monte Carlo simulations. It's worth just pointing out some of the key differences between these approaches. Monte Carlo simulations have no time component. So it's just random steps in space, whereas molecular dynamics takes a step in time to generate the next configuration. The key effect of this is that Monte Carlo simulations can't be used to calculate time-dependent phenomena. So if you want to calculate things like diffusion constants, then Monte Carlo is not going to be able to do this. Interestingly, Monte Carlo has no kinetic energy component, so this means that it's actually computationally faster to do Monte Carlo because you don't need to calculate forces and so on, you just need to calculate the energy. So this makes it fast, but it means that you can't get things associated with the motion of molecules either. Well, motion, if you think of it, is movement of a component as a function of time. So again, we don't have this time component in Monte Carlo. One of the advantages, though, of Monte Carlo is that it can jump over large energy barriers. So you could move a part of a molecule a bit, and this could correspond to a position in a completely new energy basin on your landscape, and you've just gone from one step to the next, from one energy basin to the next. Monte Carlo can do this, but molecular dynamics can't necessarily do this, because if it's a high energy barrier, then it will require a long time before it actually has enough energy and has the probability of going over this barrier. So Monte Carlo can actually explore potential energy landscapes faster than molecular dynamics. Another issue with molecular dynamics is it's limited to certain timescales, and that's associated with the computational power available to you. So if you have a process which takes place on the millisecond to second timescale, you're not really going to be able to model this using molecular dynamics, because it would take too much time even on a huge supercomputer. So there are issues with molecular dynamics there. So there are pros and cons of molecular dynamics and Monte Carlo simulations, and it's a case of choosing the most appropriate method for what you want to do. That brings us to the end of this lecture. I will point you to the recommended reading, and I will look forward to seeing you in the classroom.